I'm actually recording for Fatima, but we can also help Max out here.
I'm Max.
And who else? It's Sam. Max, Fatima,
Stupid elbow. Stupid elbow.
So, building a caring community as we proceed forward with our chemistry learning. Dynamic equilibrium. Which one of these two is a dynamic equilibrium situation? The people on Earth or HB's teachers? Why are HB teachers a good example of dynamic equilibrium most years? So we have some number of current teachers, 43. We might retire Michael Mandel and one or two others a year. So we get rid of like 2 or 3, Josh and Tom this past year. But then as we go into the next year, we get 3 more so that our total does not change. The amount that we get rid of is balanced off by the amount that come in. It is dynamic because things are changing. It is at equilibrium because the total does not change. Write down the words dynamic equilibrium.
Oh, it's a closed system. Oh, you like music? Name every song.
So, dynamic means changing, but the equilibrium is no net change. Yeah, but
people die, but then
We should reinstate
if you want a better HB example, the HB student population versus the teacher population, that ratio is more likely to be fixed. Because the total HB population does expand every year. They're trying to cram a few more kids in here because parents really want their kids to experience the magic of what's happening right now. So that ratio generally stays the same. All right. Which one of these more closely resembles a dynamic equilibrium? The number of people in the UK versus the USA, or the number of people in Kiribas versus Alexandria? Why Kiribas and Alexandria? No. Why is Kiribas to Alexandria not a better example? Kiribas is one of the remotest islands in the world. It's in the middle of the Pacific Ocean. It's a source of like nitrates and guano from seabirds. Was one of the primary export was because you can take guano is nitrogen rich, and so it's used to make like explosives. And so like the French and English empires fought over islands like Kiribas, but now they are unimportant. So,
Are there iguanas?
why is Kiribas to Alexandria not a dynamic equilibrium? Because people aren't going to and from there. If we have dynamic equilibrium situations, ours in chemistry is going to be reactants turning into products, and some of the products turning back into reactants. Okay? There are people in the UK moving to the United States.
Get them out of here.
There's probably 1,000, maybe 10,000 people coming here. Okay? But there is probably a similar number of journalists and diplomats going from the US to the UK every year. And so there's no net big drift between us and England these days. Kiribas and Alexandria, there's nobody making that trip. Okay?
We don't know that.
I'm just going to go out on a limb here and say the number of people moving from Kiribas to Alexandria and back again each year is below 1 per year. It might be, one every couple of years. So that is why this is considered not a dynamic equilibrium, because there's nothing dynamic happening. There's nobody going back and forth. Okay.
What's a guano?
What is an iguana?
What is guano?
Guano is bird poop.
Guano. I love guano.
All right. So if we look
Guano.
at the population versus time, and this is specifically of European descent people in the United States of America, there was a time before 1693 when there was no people of European descent in the United States, and then eventually they started
1492.
coming
Why did
over.
you not-
Okay?
First in 1492.
So the number of people, this is people in the USA. The number of people in England started out somewhere here. As lots of people came to the United States, the English population may have actually diminished a little bit. And now it's, we'll say, here. This is probably, UK is probably doing a little bit better than that, but we're just going to go with this. All right? Draw that in your notebook.
I don't know how.
My hands don't work.
And then put A, B, C, and D on your x-axis.
It was 1492.
We're not worried about the time of each one of those. What we are going to talk about is when is it at equilibrium. Right? At what letter have these things achieved equilibrium? Discuss with the person next to you. Go.
D. Do people in the UK photosynthesize? You sure?
All right. So let's do the applausometer. How many people think A is equilibrium? B is equilibrium. C is equilibrium. D is equilibrium. Correct. B is tempting, but B is when these numbers happen to equal each other, but total amounts does not make it at equilibrium. Net change being equal is what makes it equilibrium. Again, we're assuming that this year, lots of people from the U.S. went to England for like vacation. Some of them went there to work. Some of them went there for like graduate school. Whatever. They're going over there. But an equal number of people from the UK also came over to the U.S. so that these two things are flat. Whenever this is a flat line, the total amount is unchanging. That's when you've achieved equilibrium. Okay? You might write a sentence about that down in your notes. Okay? No net change. 3, 2, 1. So the constants for equilibrium. Let me just try and move these up a little bit. So if we think about the US versus UK example, if we put the USA in the numerator, okay, and UK in the denominator, their current populations are something like 300 million, and the British population is something like 50 million. Okay? And therefore, that's going to simplify down to a number 6. 6 is the equilibrium constant between us and England. We end up having 6 times as much products as reactants when it settles down into equilibrium. Okay? We are going to do ours as you may remember from last year, the ratio of products over reactants. How much of these chemicals do you have in the jar when the reaction settles down? I just use that for a reaction. Reactants. 5, 4, 3, 2, 1. Here is a sample chemical reaction. Okay? If I want to write the equilibrium constant for it, okay, I'm going to say K equals H2O in brackets over H2 times O2. What am I missing?
Exponent.
The exponents. What should the exponents be in this situation?
2 on the H2O.
Right? There should be a 2 on the H2O and a 2 on the H2. The coefficients become the exponents. Why is that? Let's think about the H2O part. Another way of writing this would be H2O plus H2O. It makes 2 of those groups. If I were to write that as an equilibrium expression, those would each be in the numerator. It'd be H2O times H2O. And so therefore it's just simpler to write that as squared. Right?
C
So
plus B squared equals A squared plus B
that's almost true.
squared. That's correct.
All right. Questions on this? We did this stuff last year, but we're just touching base on it again now. Let's put in some numbers. Okay? If when we do this reaction, the concentration of H2 is 10 to the 4th, then we're going to have 10 to the 4th squared times 10 to the 5th over 10 to the 8th squared. Alright, if I raise the power to a power, what do I do with the numbers? Multiply. So this is going to become 10 to the 16th. 10 to the 4th is, 4 times 2 is 8 times, if I'm multiplying the bases, what do I do with the exponents? Add. 8 plus 5 is 10 to the 16 divided by 10 to the 13th. When I'm dividing, what do I do with the exponents? Subtract. So this is going to end up being 10 to the 3rd mg. So what we're saying here is we have 1,000 times more water than we do hydrogen and oxygen. This is probably an underestimate of what this reaction goes, how strong it goes. This is an explosion. This burns. This goes right away. All the hydrogen and oxygen, I did it for you over there last week with like whoop, when we made that little bit of hydrogen gas and we blew it up. Okay, it almost all goes. So probably these numbers should be like 10 to the 1 and 10 to the minus 3 or something like that. It's gonna be. This is an explosion. This is gonna be a very heavily forward equilibrium. Step 1, balance. Step 2, write the equilibrium expression. Step 3, plug in these values at equilibrium to get the equilibrium constant.
Which one's the which? Is this the decomposition reaction?
Yes.
Maybe it's just a backwards. Uh-oh. Wait, no. No, Disgusting. Dave, maths in 4? Maths in 4? .044.
I recommend sort of comparing along the way, talking to the person next to you about the balanced chemical equation first, and then maybe checking on the equilibrium expression. And
Wait a minute.
Okay, I agree with you.
Patient.
.004433. Not .004433.
Louise Callahan, how do I balance this chemical equation? 2 NH3s, 3 H2s. So Caleb Moran, what is my equilibrium expression for this going to be? H2 cubed times N2 over NH3 squared. And then I'm going to sprinkle in these numbers. And so I'm going to get 5.5 cubed times 12.2 divided by 3 squared. There's one of those pieces of math that I can use in my head, but I'm going to rely on Milan and his calculator to do the rest of it for me. Milan, do you have a number that we get when we do all that math? 225 is probably generous. Indeed, we probably have to limit ourselves to saying 230, since 2 of these just have to say things. Oakley dokley.
Is this the reciprocal?
If I reverse the reaction, if I then take, what do we start with? H2 plus N2 and turn it into NH3. If I write the equilibrium expression for this, NH3 squared over H2 cubed times N2, that is indeed the reciprocal of the reaction we just did. If I reverse the reaction, it is the reciprocal of the equilibrium expression. I'm going to write that as a sort of formula. The K of the reverse equals 1 over K of the forward. K of the reverse equals the reciprocal 1 over the K of the forward reaction. I also know how to give students a brief break. I'll see you at 1:15.
I'm so tired.
Everybody else is all outside. Okay, after we make the question of the day. What is it?
If Max's elbow really needs surgery.
Oh, can I do it for him?
Yeah, Simon.
Okay, can I do Max's elbow?
Yeah, you can put it in your bag. Simon.
He's got like 10 different doctors all focused on surgery, but he doesn't. Why does he not want to? I don't know, he's scared. He's a little lame.
Yeah, so that's why I want that. Yeah. Why are you so?
Why do you write like a 2-year-old?
Jesus. You wrote E starting from the bottom.
That's a D.
No, I can write it nicer. I was just right E. I'm writing it from a weird. That's why I was trying. You read the E like this. You can come from the middle.
Look how good my cursor is, Caleb. Wait, I did the Q wrong.
That's best.
Wait, no, that's even worse.
Just know you're like a second grader and you're like, you right. Come here.
He wrote his A. How he wrote his A is like this. He was like that.
Alright, so we're gonna be doing cursive. Do it in cursive.
What's the question?
I can't write on cursive. You call that
Of course you can.
I can write my name in cursive. You said that was Dean Joseph.
How do you T?
In cursive? Yes.
Oh, God,
Go back
Gabe.
and far.
Okay, Gabe. Gabe, where did you learn cursive?
Third grade.
What's the question part?
Yeah, I like the different happen.
I like the different pockets. Cursive too.
I used to be sticky cursive. I didn't like second grade.
Thinking about his dad. Yeah, I was thinking he would move. Oh wait, Jesus. Oh wait, why is it?
Will Toyful eat his arm?
That's like a.
No, how do you draw an E from the bottom like that? That looks the same as mine.
Yeah, exactly. I think he just doesn't want to.
Well,
Like I knew he was.
actually does.
Fucking
now.
Jackson.
And what?
It doesn't matter.
You really want your wives like that? Win the World Series.
No, it doesn't matter.
You should not know where to start.
Yeah, but
It's because
doctor.
now I don't have hope.
That's even worse.
Oh God, David.
Jack, why don't you?
Yeah, I'm really good at cursing.
Oh, I like the recording. I don't know if it's still recording, but you might want to talk about it. Is it still recording?
Gabriel is satisfied.
Not today.
Hello.
Yeah, I know. I dragged in the A.
How do you do it C?
It's like it's a C. I'm pretty sure.
It's like this here. I brought like way too many. It starts with an undercurve.
Too many snacks is not a bad thing.
But like I'm feeling like
Oh,
eliminated.
wow.
I don't do
I
that.
just got my signature back.
Except
I did the B wrong.
you got a big.
You told me to draw your E this one. I know it doesn't there, but that's stupid. You draw your E this one.
Keep writing cursive like that.
Yes.
writing.
No, that's wrong. Why would you do Show me your Y's. Like, this is.
Those are my Y's.
Yeah,
No,
exactly.
capital Y, capital Y.
You're joking. Okay, capital Y is just like bigger Y.
Yeah, it's just like.
No, capital Y is straight.
If you're dumb,
No,
A normal
you don't.
who draws Y's like that?
That's how I draw.
That explains a lot. Your parents are related. Yeah. That's how you draw a Y in cursive. That doesn't look like that.
Yeah, it does.
Oh, capital Y.
You're either
I.
Yeah.
I draw an I. I try to draw.
But how do you draw? S.
In cursive?
Oh, that's like start from the bottom.
Yeah.
Yeah, they don't even look like that. I'm pretty sure someone writes it just like that's the weirdest like
I'm gonna write my name.
Yeah, Z's kind of.
I know X is like this.
That's how you draw.
And you're like, you go back.
And
that's
let's come back to chemistry.
No, we didn't get a list.
Choice you made. Have a seat.
Okay, you're just gonna have to match.
Wait, what's the answer? Someone else has to
So, we resolved that the K value for this reaction was 225. We now have the reverse reaction, which is this one here. Okay. We've already determined that it's balanced by saying 3 and 2. If the K value for that first reaction was 225, calculate the K value of the reverse reaction, and then using that, figure out how much nitrogen there must be at equilibrium. Go. If we were only doing chapter 2 again and again and again. But we've moved on to chapter 15.
Yeah.
I'm a 6 cube, 120. Cube is 256. Finding Nemo. Dave, how do we even know?
What does that even mean?
Constant.
So, we determined the K of our previous reaction was 225. Figure out what the K of this reverse reaction is, and then using that to determine the equilibrium concentration of nitrogen if hydrogen is 6 and ammonia is 4. So, K was 225. K of this reverse reaction is going to be 1 over 225, which is You guys have calculators. What is 1 divided by 225? 0.0044. I'll throw an extra sig thing in there. Smile and nod, yep. 4.4 times 10 minus 2. Okay. Why are we doing that? Because this reaction is not the reaction that we did the K value for. This is the reverse of the reaction that we did the K value for. And therefore we have to do the reciprocal of its K value. Well, if you put things back on the other side and then set it equal to 225, I think that might work. If you did, if you put things back in the way they were in the other reaction, set it equal to 225, yeah, I think that might work. So the way that it's designed to work, I might be able to square that peg, but the way it's designed to work is with this one saying 0.0044 equals 4 squared over 6 cubed times x. So 16 over x times 216 equals a very small number.
I got 16 and 2/3.
16.6. Can I get an amen? I get a head nod from Leo.
Yeah, that's right.
Can I get another amen? That wasn't quite the resounding chorus I was looking for.
Amen.
What?
Hey, man. Hey, man.
All right. I feel like we're coming to that answer. Are we feeling all right on this?
16 and 2/3.
There's an Evangeline's all right face. Are we good to go? Okay, then that's the all right. All right, that's okay. We're going to make a table. This table is going to have some headers and 3 rows.
In 3 columns.
Has a header, and then it'll have 3 rows. Looks like it has 4 columns.
Reading is
We're making a little table, dude.
Speaking of rows and columns, which one's the family, which one's the period, which one's
The group is vertical. Group and vertical are both family. Period is horizontal. Period is a row.
the group and family are the same thing?
Yes.
Okay. Would have been nice to know. I think I knew that already, multiple times. What? What do you want, Jed?
Check.
Okay.
If K is small, if K is less than 0.01, okay, then we have what in terms of products or reactants? Which one do I have more of?
More reactants.
Reactants. So I have products are much less than reactants.
Oh, you did 2 arrows.
Okay, so so which one does that tell me this reaction favors? Reactants. This tells me the reactants are more stable. Reactants have more polar bonds and make them stronger, whatever it is. Okay. If K is in the middle,
Me.
or medium-sized K's. Okay. K is that you look and like, oh, that's a normal number. 4. Okay. 17. Numbers that you see in your daily life. In that case, P is basically the same as R. It favors neither products nor reactants. They are about the same in terms of their chemical structure. Thanks for your positive energy.
This is a great table, Dave.
A plus for the year.
I need it.
Okay, so if your K values are large, if you have a large K value, more than 100, that means the products are favored. The products are more stable chemically. You have a lot more products than reactants. You have over 100 times more products than reactants. That means it turns into products. This does not mean it is fast. This does not tell us about the speed of a reaction. It just tells us about when it gets to equilibrium, what the balance of it is. What do you have?
Hi, Max. Hi, Max. I can see you from here.
Okay. Here is an equilibrium expression. Let's go backwards and write the chemical reaction. Yeah.
How? Oh, and then balance it? Oh no, it's already balanced.
Sorry.
Come on, Dave.
The next one has that. The next one has that.
I did it wrong. Dave, this is your fault.
Fix it.
I'm not sure about this. Can I compare with you? Sure, Dave. Let's go look at it. That's the conversation that's imagining happening.
Dave, I did it wrong.
Rather than just like, Dave! Dave!
Nitrate with
Oh, sitting next to a beautiful girl, I can talk to her
Dave,
about
this is your fault.
things, but instead I'm just going to keep yelling at a 45-year-old man.
Correct. Dave, are you saying you don't want to help me?
Yes.
What do you mean?
I'm going to help you when you really need help with talking to people and I'm great about chemistry.
But Dave, you're the
Rather than
teacher.
just yelling at
Let's say kill it more. Simon. 2 not equals 2 no plus equal 2.
Alright, Aaron, what are my reactants going to be in this reaction?
Nitrate
You can just say NOCl. Okay? I need a little more than that, Aaron. Stay focused. I need a little more than that.
The coefficient is 2.
Alright, 2 NOCl. And Patrick, what is that going to make?
2 NO plus
Okay, straightforward. We're going to take the things that were in the numerator and make those the product, and that was the exponent is going to become the coefficient.
Oh, you read from the bottom up. Oh, God.
Right in this reaction and solve for x. Go, yes, you get to balance.
Dave, my ribs hurt.
We haven't balanced it yet. You don't get to do that.
My ribs already hurt, though.
Just think about how I'm going to balance this thing.
Thinking hurts my brain.
C3H8, what is that called?
Propane.
Benzene.
What's in those canisters over there?
We blow it up.
6 plus 4 is 10. 5, I balanced it.
4, 2. Oh. Wait a minute. No, it's not. 6. Dave, what's 6 plus 4? 11 or 7. I need that slide rule to figure it out. Max has the answer guano.
We should tell Max.
Guys, what's the doctor's name? Mr. Guano. He has a guano.
Simon, what are my reactants going to be in this reaction?
C3H8 and coefficient 5 1 2.
Okay, way to ruin the surprise. And what are my products going to be, Sadie?
3 CO2 plus 40.
And once we have the chemical reaction written, we know that we have to go back and solve for this, and it turns out to be 5. Any questions on this?
With your problem.
Here's a reaction. H2 plus I2 makes 2HI. Okay.
That's facts. All facts, no
If
printer.
our K value for that equals 0.25 equals 1/4, what would it be if I doubled this reaction? If the K was 2H2 plus 2I2 makes 4HI, okay, First, let's write the equilibrium expression for the top one, for our key reaction here. It is HI squared over H2 times I2. That equals 1/4. Write the equilibrium expression for the red reaction. Somebody else's job to teach you that. 6 years ago. Maybe 8 years ago. There are kids in my son's 3rd grade class who are still having trouble writing. All right, Leo, what would the equilibrium expression for this red reaction be? How, Eli, does this red one compare to that green one? What do I have to do to the green one to generate the red one? I have to raise it to the power of 2. Okay? I have to square the green one in order to get the red one. I'm doubling the coefficients. So therefore, if I want to get the k for this, I'm going to do the same thing to its k number here. It's going to be 1/4 squared, which is 1/16. If I double the reaction, I square the exponent. So, thinking about that, if I have the reaction and reverse it, write the reaction halved and reversed. Go.
Good, Dave. I'm illiterate. Wait, which reaction?
The first reaction, I want to have it and flip it. Go. You will have fractional coefficients. It's
That's
okay.
illegal.
I'm authorizing you now.
Aaron, that's the wrong one.
Maybe if you're the deacon of a church, you can get away with anything like Aaron can.
Let's go. I'm going to take a wild guess.
Write this
It's
reaction
broken
reversed
plastic in there
and
somewhere.
halved.
No, you should rattle a lot more. You wouldn't happen to have a screwdriver, would you?
I do.
Never mind. I forgot to reverse it. Yeah, it's just you're right. Yeah, exactly. And then you're the product. Yeah, that's perfect.
If I have and reverse, this is going to be HI is in equilibrium with 1/2 H2 plus 1/2 I2. If I write the equilibrium expression for that, it is going to be H2 the 1/2 I2 the 1/2 over HI. How does this relate to our original equilibrium expression? It is the reciprocal and the square root. So I'm going to take 1/4 and I am going to raise it to the negative 1/2 power itself. I'm going to flip it and it becomes 4. I'm going to take the square root and it becomes 2. Whatever you do to the equation, you do to the exponent. Okay? So therefore, when we doubled this, we squared it. When we have to reverse, we raise it to the negative 1/2 power. Let's write that down as kind of like a sentence. Okay. Whatever you do to the equation, you do to the exponent in the K expression. So you can save yourself sort of writing out a lot of stuff if you just remember that rule and just go ahead and apply. Oh, I flipped it, so we did reciprocal. Multiplied by 2, so I'm going to square it. So it's the square of the reciprocal, and then you have that numerical value. Carefully. Very carefully.
You start from the top or the bottom?
You're asking me about like a handwriting activity? That's not my strength.
Well, no. You start from the top, go down, around.
What are you doing?
That's how you're trying to eat.
That's not.
Simon goes like this.
That's so inefficient.
You're inefficient. Your jawline is inefficient. Yeah, it doesn't feel too good, does it? Fully. You start at the top, and you go down, back around, back. Tip it, so you go. It's everywhere. Oh, you mean like this?
That's so much more efficient.
Oh, you mean like that? That's a 3. That is a 3.
This is better to start to move on.
Dave, you're smart learner.
I love how distracted.
Dave, your smart learning subscription will end in 14 days. What are we gonna do?
Keep learning chemistry, I guess. All right. We're going to learn the chemistry all we can before this thing gets rebooted by someone at the central office. All right.
No, like you said.
Write down this chemical reaction.
No.
Mg plus HCl makes H2 gas and MgCl2. This is the reaction we're going to do in the lab tomorrow. Okay.
What?
So, writing this reaction down.
Oh, because it's illegal.
Okay. So,
It's valid. It's not valid. Put it to
this reaction I did for you back over there. Okay? And it like bubbled away. Does this reaction, yep, tomorrow's a Thursday. Does this reaction tend to go forward or backwards? What do you think? Forward. So which side is favored?
Forward.
That's right, the
Backward.
The product side is favored. Which reaction is stronger? The forward or the reverse?
Forward.
The forward. Okay? You know that this reaction tends to go forward. You know that it, right? You can see it happening. So therefore, we can expect that it has what kind of K value?
More than 1.
Big. Okay? So K equals big. I'll make up a number and say 2.7 times 10 to the 5th. Okay, just some big value there. Okay. Again, I just made up 2.7 times 10 to the 5th. It's kind of off the board. So if I were to write the equilibrium expression for this reaction, I would say K. Please go ahead and balance. There, done. So H2 times MgCl2 over Mg times HCl squared. I know it's not true. We're going to talk about why it's not true in a sec. As this reaction happens, we're going to consume some of the magnesium out of this pile. We're going to react away some of the HCl from the liquid. We're going to make this gas and this dissolved ion. When we start, the magnesium has a certain concentration in the area where it is. There's a certain number of grams per unit area that is there. And there is a grams per milliliter that is there. We could divide that by its grams per mole of magnesium and get the moles per milliliter, the moles per unit area. Okay. That is its concentration. That would be its molarity, essentially. That's for a gas. This is a solid. Okay. So we have the concentration. The amount of moles of magnesium sitting in that pile is going to be the same pretty much no matter how the pile is. You could pull out some engineering business of if the pile gets really big, it's going to start smushing. And if it was like a glacier of magnesium, it would smush and compress the bottom things into a greater concentration. But for our purposes of I have a scoopful of magnesium, I'm putting it someplace. That scoopful has the same concentration all the time. Okay. Let's make up a number for that concentration. How many moles do you think are in a liter? Think about a liter of chemical. Okay? Think about a liter of solid. That's a lot of grams. That's a lot of moles. So let's say that the moles per liter of a pile of magnesium is something like 20. Okay? 20 moles per liter. That is a fixed, constant number. And so we have this expression, K, which I arbitrarily made up was 2.7 times 10 to the 5th, equals the concentration of the MgCl times the concentration of the H2 over the concentration of the HCl squared times the concentration of the magnesium solid. But I'm saying that the concentration of the magnesium solid is not going to change. Its concentration is not going to change. The total amount of it might change, but the number of moles per unit area is going to be the same no matter how big that unit area is. Smile and nod. Okay, so I can put 20 in here. This is not a good-looking algebra expression. Okay, what is the problem with this expression? I can simplify this by combining my like terms. I can combine this constant and this constant over here. I can multiply both sides by 20. And I'm going to get a new number, 5.4 times 10 to the 6th, which equals magnesium chloride times hydrogen over HCl squared. This second number is the one we tend to use. We tend to take anything that is a pure solid or liquid, and because pure solid liquids, their concentration is not changing, the amount of water in water doesn't change. Okay? If you have a cup of water, that has a set number of moles. If you have a milliliter of water, whether it's in a big cup or whether it's in a small amount, that milliliter of water contains the same number of moles all the time. So therefore, these numbers get factored into this. So when you look up a constant, when they give you a constant fraction, it includes the solids and liquids. So when you're writing the equilibrium expression, you only write it for the aqueous and the gaseous terms. You don't include the solid liquids. So the aqueous, the amount of HCl can vary. You have different molarities. The amount of hydrogen gas in an area can vary because we can increase the pressure, decrease the pressure of hydrogen gas that's there. But the amount of solid in a pile, no matter how big that pile is, the number of moles in that 1 milliliter is not going to change. Smiling non? So the amount of solid in a unit area is not going to change. If that pile was twice as big, inside that milliliter, I would still have the same amount of stuff. So I don't include the solids and the liquids because their concentration doesn't change. If you want to know the background why, this is the background why. For the rest of the chapter, we'll just start doing it. But for this first day on a unit, I try and give you guys some background and context that can help you do things. Let's see. We already got this. This is sort of doing this same math, but doing it for real. Trying to look for if I got anything good in here for you guys. Write the equilibrium expression for this reaction.
But Dave, I don't know how.
False.
No. False.
Z to the fifth over x cubed is correct.
You're late, Caleb. You're an hour and 45 minutes.
Alright. Write down Kibner.
I can write big. No sniffing in the stall.
The equilibrium expressions that we have just discussed have been K sub C's, okay, which means K is in terms of concentration. What are the units on a concentration bracket?
Molarity.
Which means what?
Moles per liter.
Moles per liter. If we are dealing with a gas, we will tend to do it as a K sub P, which means we're going to be talking about its pressure, generally in ATMs. We need to relate pressure to moles per liter. We're going to do that with our friend Pivnert. And if I want to get P by itself, P equals, I'm going to do N over, I'll start out like this, but then I'm going to get molarity as a part of this. What do I have to do to separate out the molarity part? I'm going to just combine these two and leave those on their own. So I'm going to get pressure equals N over V times RT. Write that down as an equation. P times N over V equals P equals N over V times RT. Okay, so if I apply that to my equilibrium expression, the Kp relates to the K sub C times RT. But it depends on how many KCs I have. Right? Because these each molarity has to get canceled out.
Wait, how do you do that? Oh, I got it.
Right? If we look at this problem, where to go? If we look at this problem that we're dealing with right here, Okay. How many factors of molarity am I going to have in the numerator? 5. So this is molarity of the fifth. How many factors of molarity do I have in the denominator? 3. How many factors of molarity are there in the K expression? 2. The units on this KEQ is molarity squared. So I need to multiply it by RT squared. Okay, to get the K sub C times RT whole thing squared equals the K sub P. Because these are gases, I would want the pressure expression, and I would get that by multiplying by RT squared. Okay? If we go back to this equation here, oops, go back to this one here, it is RT to the delta n. Whatever the change in the coefficients is, the delta in the n values, that is what I would want to multiply by. We're going to do another example here. 3, 2, 1. Does this one actually have anything interesting?
No.
No. What is the sum of the coefficients of the gases in aqueous on the left side?
2.
What is the sum over here?
Also 2.
Also 2. So in this case, the delta n equals 0. And so therefore, we would multiply, if we knew the K sub C, I want to multiply that by RT to the delta n. I'm going to multiply it by RT to the 0. Anything to the 0 power is
1.
So if the coefficients exactly match each other, then K sub P equals K sub C. The pressure equilibrium is going to equal the molarity equilibrium. But that's a rare instance. Normally, they do not match. If this were a G, and I'll just make up some numbers here. Let's say our K sub C equals 5.0 times 10 to the third. And we're at a temperature of, Evangeline, make up a number. What's our temperature? 10 Celsius.
10 Kelvin.
Okay.
10 Kelvin.
Solve for the K sub P. Notice I've changed this to being a G here. Go. Solve for the K sub P.
K sub C 5 times 10.
Nope. K sub C is 5 times 10.
That's what I said.
Sorry. I didn't hear it. It's in K sub P. P and C sound similar.
Why don't we change it to a different letter that doesn't sound like B or E
For pressure, that would be weird.
or G? Dave, I can't read.
So far, there's only been one time we're using 8 pi. We will not be using 0.08206 for like weeks.
Is this big number?
Wait, 8 pi?
Not using 8 pi.
Okay, I got the wrong number. 2,699,393. But that's all.
I have no idea what the right value is here. But
Who's you get?
she's right here.
Yeah, who did you get?
Beautiful girl, my same age. I look forward to talking to every day.
Is this in Kelvin or Celsius?
It's in Celsius.
Are we supposed to do it in Celsius? Kelvin? Just told me I did it wrong. I got 2.7 million.
My bad. 2.699. Where?
I changed that to yes.
Oh, Dave, how could you?
I want us to do something different. How do you guys think about this stuff?
If you know I'm blind.
Where does it say that? Oh, when you added 4 to it? Why would you do that? Oh my god.
So it'd be different. So you guys could think about it.
Dave, you know, thinking is not my strong suit.
False. Not talking is not your strong suit. Thinking you're pretty good at.
What do you do with that negative 2 value? What do you even do with that?
Uh-oh.
What do you do with that negative 2? Oh no.
What'd you get? 9.26. I got 26.999.
What is my total like number of molarities here? Where's my coefficient gonna be? This is gonna be like molarity to the 5th over molarity to the 7th. So this is gonna be 1 over molarity squared or molarity to the -2. The net change in the coefficients, it goes from 7 to 5, so the delta n is -2. So in this case, the k sub p equals 5.0 times 10 to the 3rd. Is that what I gave you guys? 5.0 times 10 to the 3rd times 0.08206 liter atmospheres per mole Kelvin. Mole Kelvin times 283 Kelvin.
0.15.
All of that to the -2 power.
Oh.
The delta t in this case is -2 because that was our delta
not the
n.
5.0 times 10 to the 3rd, just those 2 things?
Yeah, just those two. It's RT to the delta n. So, 0.08206 times 283. This should work out to be a fairly reasonable number. What is it?
9.26.
Is that before you squared it and stuff?
Oh.
Oh.
Okay. 0.08206 times 283.
23.2.
23.2. Can I get an amen?
And
I
then
got 9.2.
Okay. So, I have 5,000 times, this was what to the -2 power?
10. 23.2.
Yeah.
23.2. 23.2 to the -2 power is going to make a fairly small number. So doing 1.9 times 10 to the -3rd.
No.
Yeah.
Okay. So that times 5.0 times 10 to the 3rd. This works out to be kind of nice.
9.26.
These are going to cancel each other out. And I have 5 times 2, which is going to be around 10. So this is 9 point what?
7.
9.26 would be the K sub P. Okay? The K sub C was 5,000. That goes forward strongly. The K sub P is only 9.26. Not a big change. Here is the lab that we are going to be doing tomorrow. Take a look at that back.
That's graphite.
You are keeping your partners. In an unrealistic expectation of what I can do, I'm going to keep you on a notebook. You'll see that I graded the most recent lab. I still have one lab, like the Gatorade lab, hanging over me. I'm going to try and get to those. I'll do my best amongst other evening activities.
There's not enough